Hello everyone and welcome to your Unit 5 review video key. What an exciting time to be alive. Let's just get started. So cube root of negative 64. When you cube root, fifth root, seventh root, any odd root, you can always odd root negative numbers because an odd number of negatives multiplied together will still equal a negative number. So this answer is simply negative 4 because negative 4 times negative 4 times negative 4 is negative 64. On a problem like number 2, I like to just focus on one variable at a time. So I might look at this x. The x's first. I do notice that I have x to the first on top and x to the first on the bottom. So those are actually just going to cancel. So those are gone because you can divide them by each other to get 1. Technically they turn into 1, but then you're multiplying by that 1. And then I look at the numbers separately. We have 4/16, which can be reduced to 1/4. And then I also notice that I have y to the negative first and y squared. So there's a couple ways you can attack that. You can subtract the exponents because you're dividing with the same base. So you can do negative 1 minus 2. But since I have a negative exponent, the first thing I like to do with negative exponents is move them down to the bottom in this case, or if it was a negative exponent on the bottom already, I would move it up to the top. And in either case, 4/16 gives me 1/4. And then moving this to the bottom will make it y to the positive first, giving me y cubed on the bottom. So the final answer is just simply 1/4 y cubed. All right. On number 3, again with numbers here, you need to know what a 2/5 power means. And that's the same thing as the 5th root of negative 32 squared. Notice how I put the negative 32 in parentheses. That's important because the negative should also be getting squared, which will turn this into a positive answer overall in the end. But you can also root before you square, which makes the problem easier because the numbers will be smaller. So the 5th root of negative 32 is negative 2. So this is just the same as negative 2 squared, which is 4. And you can actually just type those on a calculator if you were doing these by yourself and you want to check. That'll be a non-calculator kind of question on the test though. Same with this one. This is cube root of 27 squared. You don't even need to write it like this. Like if you just know what this means, you can go straight to the answer. But it's good practice to write it like that because that might be a question on a test. And I'm going to cube root 27 to get 3, and 3 squared is 9. Okay. Number 5. Since these don't have the same base, there's nothing you can do with these exponents. Like we can't add 2/3 and 1/4 because 4 and 5 aren't the same base. So I'm going to do what's kind of like we say distribute this. It's not really distributive property, but it behaves the same way. So I'm going to do 2/3 times 3 to get 4 squared, and 1/4 times 3 to get 3/4. And then there's really nothing you can do from here. I mean, you can rewrite 4 squared as 16, and then you can rewrite 5 to the 3/4 as 4th root of 5 cubed. But anytime your root is higher than your exponent, there's no simplifying that you can actually do there, which is the same thing as saying if your numerator is less than your denominator, you can't actually simplify. So you can either write it like this, or you could write it as just 16 times 5 to the 3/4. But you can't multiply 16 and 5, so just be careful of that. That's what students tend to do sometimes. One explanation I like for why you can't do it is this number isn't actually equal to 5, because it's 5 raised to some power first. And so you can't multiply by 16 by 5. You would have to multiply 16 by whatever this equals as a decimal, which is not what we're doing in this section, but that's why it doesn't work. Okay, when adding or subtracting radicals, the radicand, the number underneath the square root, has to be the same. So if it's not, you can't do anything. So rewrite 45 as 9 times 5, which you can square root the 9 and get 3 radical 5. Subtract your coefficients and you get 2 radical 5. Notice how nothing actually happens to the square root of 5. When I add or subtract, it just stays square root of 5. It's just combining like terms really there. On a problem like this, since I'm raising something to a power, I would probably write this as fractional exponents first. So it's x to the 4/3 times x to the 5/2, and all of that to the -2nd. You can now either take the -2 and kind of distribute it there, or since we do have the same base now, you can add the exponents. So I'm going to add the exponents first just because I figure show it a different way than I showed it last time. So if I add 4/3 and 5/2, this is 4/3 is 8/6, and 5/2 is 15/6. So I get 23/6. So it's x to the 23/6 to the -2nd. And now you can do the power to a power rule and multiply. And -2 times 23/6, you can reduce the -2 and the 6 to get x to the -23/3. And then a negative exponent just means put 1 over that number instead. So that looks like that. If it would auto rectangle for me. Yay. All right. Numero 8. Very straightforward here. What we did in the last problem, actually, we have the same base, so we can just add the exponents. So this is x to, or 2/3 plus 1/5. And 2/3 is 10/15, multiply top and bottom by 5. 1/5 is 3/15. And so it's just simply x to the 13/15. Just adding the exponents there. Number 9, since we're cube rooting, we want as many perfect cubes as we can possibly get, including out of the number 32. So we know the cube root of 8. So I'm going to rewrite this problem as the cube root of 8 times 4, and then x cubed times x, y cubed times y cubed, and then z cubed. That's 6 z's, that's 9, that's 12, that's 13. And so you don't have to write it all out like that. I'm just showing you that on the video key. But now you can cube root all the perfect cubes, which are all of these things. And they all come out of the cube root and get multiplied. So now we have 2 from the 8. And we have a single x coming out. And then 2 y's, so y squared, and 1, 2, 3, 4 z's. So it's 2x y squared z to the 4th, but we didn't do this, we didn't use that, we didn't use that. So all of that is still under the cube root. And you get 4x z under the cube root. If you remember the shortcut, you can just divide 13 by 3, and you get 4 with a remainder of 1. So here's 4, and here's our remainder of 1, has to stay under the cube root. And you can do that for all the variables. Number 10, the square root, same thing we just did, except smaller root. So we know 8 is 4 times 2, so we can square root the 4 to get 2. A square root of a square just cancels, and you get x. You can divide this by 2, get a remainder of 1, so 1 with a remainder of 1. So, whoops, that should be a y. And that leaves us underneath the 2 from the 4 times 2, which is 8. All the x's are gone, and you have a y underneath. Okay, number 11. This one's a little bit crazy, but I would kind of simplify this first. So it's going to be 8 to the 1/3, which means cube root. So I'm not doing anything to the top. And then cube root of 8 we know is 2. And then I'm going to multiply these exponents to get -4/9. Oops, y to the -4/9. And then x to the 2/3 from multiplying these exponents together. And then it's a 9, that doesn't look very nice. That kind of looks the same. And then since we have instances of more than one instance of the same variable, we can do properties of exponents. I'm going to move this 4/9 up here first, and then add to it 2, because those things will get multiplied together, which means we add the exponents. And so that will get me y to the 2 plus 4 ninths. 2 is 18 ninths, so it's y to the 22 ninths. And then we still have that, the 2 is going to remain on the bottom. And now we have x to the first, and you can subtract 2/3, giving us x to the 1/3. And that, anytime you do the subtraction, subtract the top power from the bottom power. So this exponent minus this exponent. The answer goes on top regardless of whether it's positive or negative, and then if it's negative, you can move it to the bottom. So it's always the top exponent minus the exponent there, regardless if it's positive or negative. All right, this is adding radicals. So this is similar to a problem we did earlier. We need to make 81 27 times 3. A quick hint on this one is there's nothing we can do if I can't turn this number into a 3. So try to divide it by 3 and see if you get a perfect cube. If you do, great, then you can do it. If not, you can't do anything. So the cube root of 27 is 3. So we have 3 cube root of 3 plus cube root of 3 is equal to 4 cube root of 3. And there you go. All right, so now perform the indicated operation, state the domain in interval notation. In number 16 and 19, perform the composition, state the domain for number 18 and 19. So we got some weird directions here, but all right, so g of x is 2x plus 3. So it's just 2x plus 3 minus h of x. So put h of x in parentheses, square root of x plus 2, because that negative sign needs to get distributed. So it's 2x plus 3 minus square root of x minus 2, which then is 2x minus square root of x, and combine the 3 and the 2 to get plus 1. And that is it for that one. And then we need the domain. So the only thing going on here is we have the square root, and we can't square root negative numbers. So our domain has to be x is greater than or equal to 0. So 0 to infinity because of that square root piece. 14, g times f. So it's 2x plus 3 times x squared minus 5. And now we're just foiling, getting 2x cubed minus 10x plus 3x squared minus 15, which in standard form is 2x cubed plus 3x squared minus 10x minus 15. There's not even anything to combine there. And this is just a cubic, and it came from multiplying a line and a quadratic. All those things have a domain of all reals. So that is in interval notation, negative infinity to infinity. That wasn't close enough to a rectangle. All right. Then we got to do f divided by g, which is x squared minus 5 divided by 2x plus 3. And that's all you can do there. There's nothing to simplify or anything like that. You can't cross out. Whoa, what did it think I tried to do there? You can't cancel anything from the top and bottom because nothing's factors. So like you can't cancel an x and an x because it's not x times and the whole thing up here. It's not another x times everything down here. What I mean is if we had this whole thing times x and this whole thing times x, now these x's would be able to cancel. But in this case, we don't have multiplication like that. And then our domain, we're not allowed to divide by negatives. So you set the bottom, or sorry, you're not allowed to divide by 0. Holy cow. So set the bottom equal to 0 to find what x is not allowed to be. So we find x equals negative 3 halves from that, which means x is not allowed to equal 3 halves. And so in interval notation, that's negative infinity to negative 3 halves, union negative 3 halves to infinity. And that's our domain. Okay, 16, f of g of 2. So remember with the composition of functions, you take this number, plug it into function g first, get that answer, and then plug it into f. So if I plug in 2 right here, I get 4 plus 3 is 7. So I'm going to plug in 7 over here and get 49 minus 5 is 44. Okay, so you just start on the inside, work your way out. work your way out. F of 2, plug in 2, you get 4, minus 5 is negative 1. Take negative 1, plug it into G, and you get negative 2 plus 3 is 1. Ah. Whoa. All sorts of crazy things. All right, 18 is f of j of x. So now you take this entire function and plug it into this entire function. So this is going to become square root of x minus 1 squared minus 5. I'm just taking this and placing it for that, replacing x with that. And then you square the square root, which just gets you x minus 1 minus 5, which is x minus 6. Now that final answer is a linear function, which has a domain of all reals. But remember, we started with j of x. So here we got to make sure we don't get negatives. So you got to start at 1. So our domain is 1 to infinity. Even though our final answer looks like it could be anything. You got to start with what you did as the innermost function. And then g of x. So it's going to be a line plugged into a line. So the domain is going to be all reals because of that. And if it helps you, you can rewrite g of x like this, because we're going to take this function and plug it in for that x. So g of x becomes 2 times 2x plus 3 plus 3. And then we can just simplify that. 4x plus 6 plus 3 equals 4x plus 9. Our domain is, like I said at the beginning, negative infinity to infinity. Okay, verifying things are inverses, we need to show f of g of x and g of f of x. So f of g of x, taking g, plugging it in right here. So you get 3 times x plus 4 over 3 minus 4. So you're multiplying by 3 and dividing by 3, so those just cancel, leaving you with x plus 4 minus 4, which does in fact equal x. And then we got to show it the other way. And if they both work, if they both equal x, then they are in fact inverses of each other. So I'm taking f, this function, plugging it in for that x. So it becomes 3x minus 4 plus 4 over 3 equals 3x over 3 equals x. And so since they both equal x, they are inverses of each other. You should write a concluding statement. Since f of g of x is equal to g of f of x, and they're both equal to x, f and g are inverses. Yay. All right, now let's actually find an inverse. So switch x and y. This says f of x, but you can call it y. So x equals y to the 4th plus 5. Subtract 5. 4th root both sides. Now technically, since we did an even root of both sides, you should have a plus or minus. But this is the domain restriction on this to make this a function. So since x has to be negative, then our y's on the inverse have to be negative. So instead of plus or minus, you just put the negative case. And that makes the original function pass the horizontal line test, which makes the inverse pass the vertical line test. I'm going to use the inverse notation right there. Because I can't really call it y, because it's a different y than from up here, even though it's called f of x, I guess. And same thing over here. We're going to switch x and y. So x equals 3 halves y cubed plus 4. Subtract 4, giving us this. You can multiply both sides by 2/3. So it's 2/3 x minus 8/3 is equal to y cubed. And now you can cube root both sides. So y equals the cube root of 2/3 x minus 8/3. No plus or minus on this one, because when you odd roots, you don't get a plus or minus. Okay. The graphs I'm just going to talk about real quick. You can sketch the graph, or you can look at the graph on Desmos or your graphing calculator. But remember, this shifts the graph up 2. This stretches it by 4. This number is going to move a graph left 2, stretch it by 1/2, so it's actually a shrink in that case. This flips it, and then this moves it up 4. So always do this transformation last. Okay, but again, you can just use Desmos for those. Save you a little time on the video key here. And now let's solve some equations real quick. Always check for extraneous solutions. I'm going to skip the checking extraneous solutions part on the key, or on the video key at least, and you can check those yourself. So first, to get rid of a 5th root, since the whole thing's already by itself, you can raise both sides to the 5th power, giving us this. Add 8, and you get x equals 10. Again, plug that in, make sure it works. If it does, great. If it doesn't, it's extraneous. This one, we're going to square both sides because we have a square root, but first you got to get rid of the plus 3. So you get square root of 8x plus 9 is equal to 3. Square both sides, giving us 8x plus 9 equals 9. Subtract 9, giving us 8x equals 0, so therefore x equals 0. Plug it in, see if it's extraneous or not. On this one, since you have a square root equals a square root, you can just square both sides or use logic and say, hey, square root of a number equals square root of another number, so those two numbers must be equal, which are 7x minus 7 and 3x minus 2. And now solve this, so I'm going to subtract 3x and add 7, so 4x equals 5, and so x equals 5/4. Okay, so not too bad on a problem like that. It really just turns into a relatively simple equation here. Double checking my work in my head. I think I did that right. Okay, on this problem we have a 2/3 power, but we have this 1/2 out here. So multiply both sides by 2 first to get rid of that. And you have 5x plus 7 to the 2/3 equals 9. Now raise both sides to the 3/2 power to get rid of the 2/3 power. So it's 5x plus 7 equals 9 to the 3/2. 9 to the 3/2 means square root it, then cube it. So you really have 5x plus 7 equals 27. Subtract 7 and you get 5x equals 20, and so x equals 4. It didn't like my rectangle again. I thought that was a pretty good one. Oh no, that's twice. Third time? That was the worst of all my rectangles and it liked it. All right, last problem. This is going to be the most complex one because we have a square root equals something over here, so we got to square both sides, which means you have to do x plus 1 squared. And then over this side, that's the same as before, where it's just 19 minus x. So now we got to square this and get x squared plus 2x plus 1 equals 19 minus x. Now we have a quadratic. So set it equal to 0. X squared plus 3x equals minus 18, sorry, equals 0. So that's me just moving this over here and this over here. And then 6 times 3 is 18. So you can get x plus 6, x minus 3 equals 0. And then therefore x equals negative 6, positive 3. Check for extraneous because I think one of those is going to be extraneous. So make sure you check it. All right, that is it. Hope you enjoyed it. Good luck on your test.